afternoon. Welcome to the AS seminar. Today we're very pleased to have our own Marat Khairoutdinov to present the seminar. Marat got his master's in physics in Moscow Institute of Physics and Technology. After that, he stayed a few years in Moscow, working as a research scientist with the Central Aerological Observatory in Moscow. Before coming over to the US and obtained his PhD in the University of Oklahoma. After that, he joined CSU, Florida State, and has been a research scientist there until 2007 when he joined us. So it's been 8 years, more than 8 years since he was working here. So, but he joined us as a sort of joint appointment between SoMAS and the Institute for Advanced Computational Science. And well, I think most of us know him quite well, so I don't think we need to go into details, but let's get going.
Okay, can you hear me? Thanks, Edmund. Okay. Yeah, it's been it's hard to believe that it's been 8 years since I was here, so it's kind of awkward for me to present seminar, to be honest. Usually like sitting there. Okay, so let's see how it goes. So I'm going to talk about, well, I've been thinking a lot of what I'm going to talk about. I've been working on quite a few things lately, and so I probably can give several seminars, but I chose this one that's why this generic title that can be like for any seminar, because I didn't really know what I'm going to talk about. So, but I decided to talk more about aggregated convection and simulation of aggregated convection in tropics, and in the context of a problem of why tropics are so resilient to global, has been so resilient to global warming in the past, and probably going to be resilient in the future. And one of the hypotheses that we have is that it's because of aggregated convection, and I'm going to talk about that. And my tool is, of course, cloud resolving model. I'm actual modeler. I actually code models. I don't just use them. And so I know them from inside out, and that's probably why it allows me to use them in some kind of creative ways, because I'm not afraid of them. And I'm not afraid of using a large number of processors. And I know some of you probably have this computer phobia, that you like when you can allocate 5,000 processors, you would rather not. You would allocate like 100 processors, right? Processors. I don't have this computer phobia. So if I had like 100,000 processors, I would use 100,000 processors, no problem, if my model could use them, of course. And then you can get, actually, by doing so, you can get some unexpected breakthroughs when you use model in some unusual creative ways. And some of those I'm going to show today. Kind of interesting results, I think, that have been obtained by that. Okay, so this one, someone asked me if this previous picture was real. Yes, it's real. And this one, is it real or it's simulated? Well, it's simulated. So, and it's from one of my simulations, so-called Giga LAS, that I'm going to show a little bit today. And this done was not by me. It's from, animation, visualization was done by using some very sophisticated ray tracing algorithm that actually takes into account actual very complicated kind of tracing of photons in clouds, and you can even see horizon there, and there's also been introduced some aerosol in there. So it looks pretty realistic, and this represents only about 1/20th of the actual domain of simulation. So it's just very tiny portion of actual simulation. And it took like many hours on supercomputers to produce one image. Okay, so outline what I'm going to talk about today. First, I'm going to talk a little bit about GigaLAS as an example of application of cloud resolving model to improve parameterizations, hopefully. Then I'm going to talk about radiative-convective equilibrium over large domains with and without rotation. And finally, I will finish with some recent results of the so-called near global simulations that we've been doing recently, and as a kind of our preliminary leap forward toward global cloud resolving model. Okay. Just to motivate it, climate system like this one is a diagram that probably all of you have seen before. And I show it in my undergraduate atmospheric physics class too. And I think this one is a great diagram that shows basically the whole climate system, how it works. And the central in this picture are clouds. And not only clouds, it's all this interplay among radiation, which is actually driving the whole thing, and clouds, and water vapor, and that's very important. Most of my results I'm going to show it's interplay between those three things. And of course, we don't quite can simulate clouds in climate models, and that's why we need this kind of tools that would allow us to understand better how clouds actually work in this kind of idealized settings. Idealized models are great because they don't have all the details that sometimes cloud the picture, and allow to kind of cleanly understand what's going on. And of course, idealized simulation, sometimes it's difficult to actually explain why they're so useful. Why you don't just simulate particular storm. Well, it's just because so many things going on in particular storm, and I want to kind of take a better shot at understanding. So I'm going to talk about some idealized simulations. So atmospheric models, just to give you a perspective, here I show kind of hierarchy of atmospheric models that exist today. And so vertical axis here is kind of typical domain size, so it's going from, like, say, about 1 kilometer or so to the whole Earth. And the horizontal axis is scales of motions that resolved by a particular model. And to see that, for here it's large simulation models that resolve basically most of the eddies in the atmosphere, except for very small ones that parameterized, and then cloud resolving models that don't resolve scales like hundreds of meters typically, but they resolve scales like in the order of 1 kilometer or so. And their domain sizes are relatively small, in the order of maybe 1,000 kilometers or so. And then the regional models that, at the expense of resolution, they actually resolve bigger domains. And so on until we hit this global climate models or general circulation models that don't resolve much. The kind of typical resolution is the order of, say, 100 kilometers. Although recently there have been some progress in that area, and but those are not really typical climate models, and they typically not run for a century for this kind of cloud scale change scale. So this is kind of typical resolution of the order of 100 kilometers, and there is some kind of another approach called super-parameterized or multi-scale model, which I'm not going to talk about today, even though I probably my most contribution towards my being faculty here is probably because of that. But I kind of, frankly, I moved away a little bit from that topic because now it has been too crowded field now, and I'm trying to find some field which is not particularly crowded. And then global theorems, of course. Those are Japanese scientists leading effort in this. And I'm going to talk about these two dots here. And so this one is kind of current frontier. Basically, all models they are kind of not crossing this frontier yet, or maybe some few brave guys. And this is final frontier. This is what nirvana of our field. And after that, we can retire, basically. Everything is resolved. Everything relevant is resolved. And we don't need to parameterize, basically, except for still microphysics, right? But this one is basically what we're leading. And I think we reach this boundary in about 10 years. So I'm going to talk about those two kind of things. This one, which is called GigaLAS, which is basically like LAS, but it's getting into a realm of cloud resolving models in terms of domain size. And then near global CRM, which is like CRM, but getting into a really big domain. So I'm going to talk about the results by my model that I created back when I was a graduate student. It's called the System for Atmospheric Modeling. Of course, it has changed considerably since that time. But generally, dynamical core, for example, is pretty much the same. It's an elastic model, so there are no sound waves. It's non-hydrostatic, of course, and it can be 2D or 3D. It's using some simple subgrid scale closure schemes like Smogorinsky first order and a little bit more comprehensive prognostic turbine kinetic energy scheme. It currently uses two radiation packages from Community Atmosphere Model Type 3, which is GCM, and RTM from the more latest version of the same model. It's using several microphysical packages that you can choose, not as many as WRF, of course, but like 3 or 4 that you can choose. And basically, most results that I'm going to show here came from this single moment microphysics, which is very simple, and I kind of like it because it's very fast, and it produces kind of reasonably looking results when you test in known tests, if you use known tests for microphysics. And it's, of course, massively parallel. So this one is the first example of using CRM as a tool to understand what's going on in subgrid scale of GCMs. So in this case, it's so-called GigaLAS simulation that I've done several years ago. That basically simulates 1 day of evolution of convection over ocean in ITCZ region with resolution of 100 meters and a horizontal resolution of 100 meters and vertical resolution and boundary layer of 50 meters and 100 meters above. And it has about 1 billion grid points. That's why it's called GigaLAS. And this one is one of the first of those kinds. Now there have been quite several other similar simulations done. But the point of this simulation is that it runs over a domain of about 200 kilometers across, so which is kind of a typical GCM grid cell. So the hope is that by analyzing those kind of simulations, we could improve subgrid scale parameterizations of large-scale models. And this one is just visualization of this case for about a quarter of the domain to see better. And here you can see interplay of shallow convection, cold pools, deep clouds like this one. And so it's producing this cold pool that then makes new clouds from a region which is like you see that new cells actually have tendency to develop over the cold pool H region.
What's the light blue color?
Light blue, it's probably ice. So it's gravity waves that we see in the upper troposphere and some cirrus clouds.
So it's thin.
Yes. But you see, like it's like water surface, so it's gravity waves. Okay. So one of the, for example, one of the applications is to improve entrained and blue model. that's one of the most popular choice for cumulus parameterizations in climate models. And so this is a kind of typical Radiative-Plume equation, which is used so that the rate of change of mass in the updraft is proportional to the mass flux. I mean, of mass flux in updraft is proportional to mass flux itself. So this is kind of a typical Radiative-Plume model that started a long time ago, back in the 60s. And so you can actually do something like that. And here, what is shown here, horizontal axis here is a conservative variable, which is moist static energy, and vertical is height. And those are kind of joint PDF or of this sampled over updraft cores. So you see that clouds start kind of in this point. All of them start at one point, which is kind of interesting by itself. And this is domain mean. So you see that all plumes don't start from mean values. They start from moist parcels, which makes sense. But they all start from one point, and it's not quite understood why it is the case. And then some of them kind of entrain very quickly, so they kind of... So normally, if it doesn't entrain, doesn't mix, it will go vertically. More static energy is conserved. But you see that most of the plumes, they actually entraining, and some of them go deeper than the others, and those lines are solutions from assuming this entrained plume model for different lambda. And you see that indeed it's kind of entrained plume model can be a good approximation for this process. And if you look, you can, for example, say that, first of all, there are no non-entrained plumes. That's kind of in this simulation. And you see that, for example, in this particular case, the best actually to assume that actually your entrainment parameter is not constant, that most models do, but is actually inversely proportional to height. So this is kind of just one example that I tried to entrain my previous student, Diego, into doing something in this. Unfortunately, he graduated earlier than I convinced him to do something like that. So maybe my next student will do that. So another interesting thing, like how actually deep clouds come about, like you can now, because you simulate deep clouds with 100-meter resolution, you can actually see how boundary layers actually lead to deep convection. For example, here you see these shallow clouds developing, and then all of a sudden they kind of start merging, and then you have this deep cloud. So basically deep cloud is not really some big plume, it's many small plumes merged together by hydrodynamic forces, like when you have two updrafts nearby, pressure between them drops by Bernoulli equation, and then they just basically forced to merge. And that's what you see here. And you see how they cannibalize and kill all clouds around them. So there is this competition. Those that kind of, they work together to kill all the competition around. You can see here. And then you get deep cloud. Okay, that's very useful to run a model in this kind of simulating actual. This one is, for example, was particular gate convection kind of in ITCZ. And you can use this model and force it with observed, say, sounding, observation from sounding arrays. And that has been done considerably over the last like 20 years or so. But the problem with that approach, specifying forcing, for example, that you basically specify your solution as well, because of this balance that you need to have, for example, between conversion of moisture and precipitation rate. You converge moisture, but your adiabat cannot go too far from moist adiabat, so you basically forced to precipitate at about the same rate as you supply moisture. So you cannot really test model, and I don't show here, but you can get very ridiculous, very reasonably looking results by that framework by using, say, ridiculous settings of your model, say 50-kilometer grid spacing, and you get almost undistinguishable solution from like 1 kilometer grid spacing, which is ridiculous. And it's because you're basically prescribing solution. So I like, for climate problem, I like this another approach, which is, has been around for quite a while now. It's called radiative-convective equilibrium, or sometimes people call it radiative-moist convective equilibrium, to stress that it's actually something involving moisture, because you can have radiative-convective equilibrium without actually any moisture. So why it's such a nice framework? Because it's a very nice model of tropics. 80% of energy in tropics actually stays in tropics, but only 20%, about 20% leaks out. So in a sense, tropics are close to radiative-convective equilibrium. So it's a useful framework to study a response of tropics to, say, warming. So in a way, it's climate model analog for cloud resolving models. So this one is not initial value problem, it's boundary layer problem. So you, for example, in this framework, you compute everything: radiation, microphysics, surface fluxes. There is no transport in and out of the domain, and because you use periodic boundary conditions, for example, you don't specify any forcing, so everything is just basically bubbling in its own. And one thing that usually you only specifies sea surface temperature, and everything else is computed. And then you, for example, change your sea surface temperature and see what happens. So this is kind of example of typical radiative-convective equilibrium simulation, and you see that it's just bubbling convection and bubbles. So you have these big, like large clouds, small clouds, if you have cold pools and so on. So then you can look at certain statistics of this simulation, and that has been done very considerably in the past. Now, one interesting thing that I found accidentally back when I think it was 2001 or something, when I just got this account on big computer, supercomputer. So the first thing I did, I ran simulation at the maximum domain I could before, like size. Back then computers were, of course, much slower than today. And to my surprise, what I found is this nice bubbling convection all of a sudden collapsed on a domain big in some certain domain of certain size into this one region. So instead of like bubbling everywhere, as you saw before, it actually bubbled down to one particular region surrounded by this dry region around. So convection self-aggregated. And that's got a kind of interesting result, although I haven't realized its importance back then. Why it's important? So first, to understand why it's important. Well, of course, it's idealized. So you don't really see that maybe in nature, with the big blobs of convection. Although you do see it sometimes, but you just don't realize that they are. This is self-aggregation entropy. So this one is a normal RCE. So a few days before this aggregation. So you see this clouds bubbling, and then when it's aggregated state, and it's in the middle, it's periodical domain just because I put it in the middle. I've been always asked this question, why it's in the middle? Well, I just put it in the middle, okay, when I plotted it. And so this one is outgoing long wave radiation. And if you look at numbers, here is 257, and here is 290. So it's much more outgoing long wave radiation in aggregated state than in non-aggregated state. So basically, sky's opening up. So you have less greenhouse effect in aggregated state than in aggregated state. And that's actually very important. Then, much later actually, just accidentally again, I asked myself, what if I change temperature in wide range? And to my surprise, at certain temperature, below a certain threshold, in this case it's 297, it stopped aggregating. So it would aggregate at warmer temperatures and wouldn't aggregate at colder temperatures. And since then, there have been quite a few papers explaining that. And in a nutshell, recently, so before that, So what's happening in this, why it's so different? The difference between those two states, aggregated and not aggregated. Well, if you look at a relative humidity profile, average over the domain, you see that in a non-aggregated state, those blue lines, it's much more moist atmosphere, while in aggregated states it's dried out. So that's what that's what explains this opening of the skies. So water vapor is a very strong greenhouse gas, and reducing it reduces OLR. And this is from observations that I'm going to also talk a little bit later. This one is relative humidity versus height derived from observations for different cluster sizes. So basically you have this, you look at the relative humidity around clusters that you see in tropics of different size, and so sometimes you have many clusters in one area, sometimes it's just one big cluster, supercluster, let's call it. And you see that as you have more aggregated convection or smaller number of clusters in a particular region, you have dry atmosphere. So when it's dry, clusters become big. When it's moist, clusters become small. And that's basically what similar to this. Okay, kind of in a nutshell, what's the explanation for that? One of probably the best explanations have been done by work by Khairoutdinov, recently published paper, where he basically discussed so-called radiative, that this is a consequence of so-called radiative-convective instability. How it basically works. So when you have cold temperatures like here, what is shown here, horizontal axis, is the heating or cooling rate by short wave, this is 0, and long wave radiation, black is net, and this is height. So it's for two temperatures. For cold temperatures, sea surface temperature of 25 Celsius, and here it's very warm, for 40 degrees Celsius, just to have this kind of complete opposite. So you see that the effect, for short wave, it's kind of always have this, oh, by the way, what's it shown? This is perturbations when you decrease moisture abruptly by 20%. So basically in clear skies, so there's no clouds. That's basically what is drying. Remember that picture I showed before, how it starts. It starts with this drying patch here. Drying, this is precipitable water, so it's water vapor. And then here is moist air. So you see, but it starts as a drying of certain regions, cloud-free regions. And this drying is kind of basically progressing. So there is some kind of instability here. And that's what's basically happening here. That at cold temperature, this is change in heating rate because of this drying, initial drying that you impose on the system. You can see that when it's cold, your water vapor amount is relatively small. So when you decrease water vapor, you basically decreases everywhere, and the effect is basically linear to that you have less emitters of infrared radiation. So your cooling is actually decreasing, which is, in terms of perturbation, it's positive perturbation. So it's kind of, it's positive, it's like warming. So less cooling, it's like warming. And that actually, and less warming if you have this dry patch, and it's usually associated with down motion. So less warming, it means that it's actually opposite, it wants to go up. So it's negative feedback. So it gets rid of those patches, doesn't allow them to develop. So at cold temperature, because of this long wave feedback, at warming basically, when you have dry atmosphere, it warms low troposphere, relatively. So which means that it's actually negative feedback to drying by downdrafts. At the same time, if you actually switch to much moist atmosphere, and this is radiative-convective equilibrium, so atmosphere becomes really, really moist. By Clausius-Clapeyron equation, remember, it's like increase is exponential with temperature.
Change the sea surface temperature.
Yes, This one is surface temperature change, and then you run it to equilibrium, and then you dry it.
My question.
Yes.
You change the sea surface temperature. Do you hold constant the relative humidity
No.
above it or the specific humidity?
No, you don't hold constant anything. You just run it to equilibrium, and then you just reduce your water vapor by 20% everywhere instantaneously, and you compute instantaneous heating rate because of that. So you don't run to equilibrium again, because it will then return back to normal.
So 20% across the
Whole troposphere, yes. So this is perfect.
Especially everywhere.
Yes.
20%.
It just no. This one is profile. This one is single column kind of thing. So it's a profile. So and then because you have so much moisture, it becomes so opaque to radiation that decreasing 20% here, where it's so much moisture, doesn't really do anything. It's already so opaque that it's like reducing by 20% is not going to change anything. But it still changes a lot, by the same mechanism above where it's much drier. So basically what you do, all of a sudden you open this window above this low troposphere for infrared radiation to escape. Because it used to be like, so this effect is kind of because of non-locality of radiation, infrared radiation transfer. And so you have this opposite. Now you have cooling because you open this window. And so you see that it's completely two different responses. And if you do it for different temperatures like here, and this is in this paper, you can take a look at this. It's in James, I believe. You see that there is this threshold temperature somewhere in the middle when this effect is basically switches from one regime to another one. So this regime is stable, RCE. This one is unstable, radiative-convective equilibrium. So there is this threshold temperature in tropics, which if you go warmer than that, it creates more aggregated convection. When you go below that, it's actually more favorable to bubbling disaggregated convection. So now, because of that, you can formulate this hypothesis, where we formulated this theory a few years ago. Basically, it works like that. That would explain why tropics are so resilient to global warming in the past. Like, for example, during the Permian period, 50 million years ago, reconstruction suggests that the amount of CO2 in the atmosphere was something like up to 8 times more than today. But temperature was only about 10 degrees warmer in the tropics, like ocean. So if you assume this normal, like 3 degrees per doubling CO2 kind of thing, it's not explained by this kind of linear that most GCMs produce. So basically, to explain it, why tropics are so resilient to warming, is this hypothesis that you have warm SST, then you have more self-aggregation, and that dries the atmosphere, and the atmosphere actually it's reducing the greenhouse effect, so you open the skies to infrared radiation, and that cools SST, because that actually allows surface to cool, and that pushes system back before the threshold, and that disaggregates, so now you have less aggregated convection, and you restore the system. So it's basically resisting warming, because as you warm it, you push it above aggregation threshold, and it starts responding by creating more aggregated convection and drying the atmosphere. So there is this kind of process, which is not, of course, in any GCM. Not a single general circulation model has this, this process. So that's a hypothesis which we've been trying to demonstrate that with various success. Now, what happens? So you were saying, well, Marat, this is just blob. You don't see blobs like we go outside. Well, yes, you do see them. Those are called tropical cyclones. So if you have these blobs, usually in tropics, if you have some rotation, you develop this tropical cyclone. So this is simulation of generation of tropical cyclone in completely horizontally uniform atmosphere. There are no waves, there is nothing. It's just bubbling convection, and all of a sudden it aggregates into this tropical cyclone. So you don't really need any aid for the spontaneous generation of tropical cyclone. And you see how much water vapor is associated with tropical cyclone. That's what's actually driving the whole thing, this evaporation from the ocean surface. Okay, so this is nice, but it's only one tropical cyclone. It's kind of difficult to study because statistics of it is kind of difficult to derive. It's just one cyclone. So we ask ourselves this question now: how to get more cyclones, so that we could say, for example, how their number changes with temperature, with sea surface temperature. Is it going to increase, decrease? After a cyclone is going to be stronger or weak, and so on. For that, we need many cyclones in one simultaneously, rather than one cyclone here. So what we did is trick. So we of course could just make domain very large domain, but that would be very expensive. So instead, we actually increase rotation of Earth several times. So in this case, it's like factor of 4, and so this is what you get. So you have suddenly more tropical cyclones. They're smaller, but they're still there. So that's the system we basically use. And we call this TC world, or tropical cyclone world. So it's world populated only by tropical cyclones. It's all ocean, so it's aquaplanet with constant SST, and basically the whole thing is rotating like crazy, and it's populated with tropical cyclones. So it's basically like extreme case of world with tropical cyclones. And we did that for various sea surface temperatures. This is just animation how it looks like when we have this particular configuration with particular sea surface temperature. And you see this last tropical cyclone spinning around, and sometimes they merge. And very resilient. It's like this one simulation like for 100 days. So for 100 days it's just spinning, 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 spinning. And what is interesting, everything is the same, but some of them small, some of them large, some of them slow, some of them fast. So you see that how then you predict, like this is about predictability of tropical cyclones. So you have absolutely the same conditions, you have the whole variety of tropical cyclones kind of developing. Now if you look at the number as a function of sea surface temperature here, so we start from 21 degrees Celsius and then increase it to 36 degrees Celsius. So basically whole range of possible sea surface temperatures in the past, in the future, in present. So what you see are two things. One, that number of tropical cyclones actually decreasing dramatically with increasing SST. But they become bigger and stronger. So they are and deeper actually in terms of pressure. And it can be shown here. So you see that number of tropical cyclones quasi-linearly drops with increasing temperature.
The question.
Yes.
So are your SSTs fixed, or
Yes.
is there interaction?
No. So basically SST here is a proxy for climate change. So you basically specify it and then you see that this is what your climate is. And cyclones you see get various kind of, at the same time as the intensity grows considerably, precipitation grows considerably with SST, and kinetic energy associated with each cyclone increases tremendously. So even though there are fewer of them, but they become on average much stronger. And this is just PDS, and this is, if you're interested, look at this paper, it's the interest of that. But it just one probably thing that you see this is wide range, let's say, you can get wide range of tropical cyclones, intensities, center pressure, and size for the same conditions. So it's just completely random in this case. So, well, I was need to skip this, and then one of the reasons why, like physical reason, why you have fewer of them, is basically efficient. Well, let me skip this. I think it's too long explanation. I suggest you look at this paper where it's actually derived. Basically, it's demonstrated that Rossby radius of deformation, for example, it's just this kind of a typical form. And then this one scales in tropics like moist adiabat. So this is moist adiabat, which is scaled like with moisture difference between, say, low troposphere and mid troposphere. This is delta Q. And so and this guy is mostly determined by surface Q, or water vapor, which is surface kind of at SST. So we predict that Rossby radius is actually proportional to square root of Q at the surface, and radius scale is actually proportional to Rossby radius. And then separation, it's like how many you can fit in domain given size. And if you do this math, you get that it's actually number of cyclones in a given domain is inversely proportional to water vapor at the surface. Saturation, water vapor at the surface. Kind of not very intuitive thing, right? But if now you plot it like that, so this is 1 over water vapor at the surface temperature, and this is temperature, and this is number of tropical cyclones in our simulations, you see that it explains it almost perfectly. Indeed, that works very well. So the warmer it gets, the more water vapor you get, your cyclone become bigger, and few of them fit in this particular domain. Now, is it really something that we can find some observations? This one is actually, I did it last year. I don't remember for what. I looked at this best track data, and this is versus SST. So this is now observations, not model. This is for last 34 years or so, since I kind of don't trust much before that, because here we have kind of satellite year. And this ocean temperature, and this is what is shown here is temperature at storm genesis, so when a tropical cyclone actually appears. And for 3 types of cyclones, one that created major hurricanes, led to major hurricanes, then all hurricanes kind of, just not only major, and then all tropical storms and hurricanes. And you can see that, yes, indeed, like in the record, there is this, of course, warming trend of SST. And also, if you look carefully, that you see that actually major storms, like this green line, is actually always because of warm SSTs at the genesis. I mean, not always, but I mean, it's a trend. So it's, there is this very direct correlation with SST when tropical cyclone form and its eventual size and strength. So warmer it gets, the bigger they and stronger they potentially can become. So it makes sense. So this one is observations. And of course, this one is observations of, that's well known. It's number of hurricanes, tropical storms, and major hurricanes as a function of time. So this one observed. And to see that there are 2 trends. All storms and hurricanes, so all the tropical cyclones, actually decrease with warming SST. So the number does indeed decrease, but number of very strong tropical cyclones, the category 3 and higher, actually increasing. So they become stronger overall. So you can see the signal already in observations, I would say. This kind of that supports our model finding. All right, now the final topic, it's so-called near global RC. What is this one? So we now do the same radiative-convective equilibrium simulation, but we are, instead of prescribing this constant SST, we prescribe some profile of SST cross from, so it's like a belt, aquaplanet. So we don't simulate the whole Earth, we simulate it plus minus certain latitude. So in this case, like 46 degrees north-south. And we specify this SST. So it's warmest at the equator, and then it's tapering off. So you see this, and then we increase temperature by 4 Kelvin as a proxy for kind of global warming. And this is aquaplanet, so it's very idealized. Now we want to see what's actually changing here. And my focus in here, there are many interesting things here you can look, but my focus here is the clusters. How the behavior of clusters changes in this case. So we have control, which is like kind of this, and it's based on so-called Q-Alps profile of sea surface temperatures that used by many GCMs in the past as a test. So we can actually compare to GCM simulations in this case. And then we increase SST by 4 Kelvin and repeat the same simulations. And domain is pretty large, and the resolution here is 4 kilometers. And horizontal grid spacing domain is something like half of the Earth in this case. So it's about 20,000 kilometers. And in the vertical, in a y direction, it's about 10,000 kilometers. So it's pretty sizable domain, and we run it like for many tens of days. So this is how one snapshot looks like. So what you see here is ITCZ in the middle, over the equator. Then you have these so-called atmospheric rivers, right? And you have these extratropical cyclones. You have these cold sectors. You have this, your cold sector convection, and you have some aggregated convection. You see that this is particularly related to Kelvin wave. So looks pretty reasonable.
Is that a pure water world, or do you have all of it?
Yes, pure water. It's aquaplanet. Yes. This is how water vapor looks like for the same image. So you see that most of it is in tropics, in deep tropics. And this is how it's if you animate it. So you see this, and it has diurnal cycle. So that's why you see this flickering going up and down like number of clouds. Because at night you have more clouds. During the daytime, when atmosphere is more stable, you have less clouds. Especially in subtropics, you can see it. So and you see this organized convection here, like these big clusters, moving to the east, which are Kelvin waves. And some of them actually, smaller ones, moving to the west. So there is this interplay of many clusters. So how to actually look at all this? And, well, it looks almost like a normal kind of general circulation model. This one, for example, zonal wind. So you see two subtropical jets here. Okay, so I will skip in the interest of time. Now, this one I'm not gonna. I was very optimistic about my time here. As usual, my rule of like 1 slide per minute doesn't work usually. Since I became actual faculty, I noticed that it broke because now I can talk whole class on 3 slides. So I kind of learned this, so I can yak, like go. So I think that's why it's kind of like I spend too much time on each slide. It's professional, probably. Yeah. So in control Kelvin wave, for example, this is our Muller diagram. So it's horizontal distance in the deep tropics. Average over deep tropics here is days. So it's about 40 days here. And you see this is Kelvin wave signal, 16 meters per second, which is exactly what is observed. Exactly. In actual true Kelvin waves move at 16 meters per second. Coupled at Kelvin waves, convectively coupled. And this one is the future kind of thing. Warmer world, you see that they move considerably faster. And that's not really, I have not been able to explain it using literature on convective wave speed because it's too fast to increase. To take into account, like, say, deeper tropics, deeper troposphere, and other things like change in moist adiabat, that cannot explain this. So something is really still needs to explanation of this. It's too fast an increase of Kelvin wave. Now, to look at clusters, I'll look at this, use this methodology by Tobin et al. And Bonny, who looked at those clusters in observations using these clouds, infrared brightness temperature, observations from satellite, and the resolution of that thing is half a degree, which is about 50 kilometers in tropics. So it's a 50 kilometer, you cannot see smaller things than 50 kilometers. So I need to degrade my simulation to actually compare. And they use like this kind of, kind of producing those masks. And so I wrote software that actually does the same thing, but with my output. So this is how you start. So this is how it's simulation. This is brightness temperature for the same image. So you see that it has these deep clouds here. So I need to degrade it now. So focusing on this only tropical regions where those deep clouds are. And this is how you go. So this is cloud mask at 4 kilometers. So it's lots of details. And this is based on brightness temperature threshold of 240 Kelvin. So that's kind of cold tops. And this is when you degrade cloud brightness scene, you get this mask, which is much less cluttered than this one. And now you can actually use algorithms to identify the individual clusters by just basically looking, well, it's very simple algorithm. Believe it or not, it's like 8 lines of code that allows you to count regions that not connect to each other. It's 8 lines of code, I swear. I didn't expect that it's so simple. But you can, for example, get this result. So you see that different colors show different clusters. So those are continuous regions which are not connected to each other. So those I call clusters, okay? And they have different size, shape, and so on. So now you can use those information, and I use 40 days, 3-hourly snapshots. So it's about 320 snapshots like this, like that, and number of clusters is something like 80,000. So that's pretty substantial statistically. Have lots of clusters. And now if you plot the size as a function, so this is PDF in log scale, log, cluster size, area of cluster in pixels, just for simplicity. And this is the number, corresponding number. So it's kind of nice linear kind of relationship until it gets to very large clusters, which is actually tapering off. It falls off. So it's not linear anymore. And this observes that I found this kind of paper by Peters et al. Recently, 2009, and this is how it looks in observations. So it's also linear, and then it's actually tapering off for the largest ones. So it kind of was very, I got very excited when I saw it. I said, oh, my model of this idealized simulation does actually something which is reasonable. Now, at warmer climate, you see that it doesn't taper off. So your number of superclusters, or big, juicy clusters, with an area of thousands of square miles, it's actually increasing by a factor of 10. While other kind of types of clusters don't seem to be bothered by increasing temperature. So they're all kind of the same on top of each other. So only big clusters increasing. Is this exactly works how our hypothesis would work, right? So you have this increase and you produce this more largely aggregated convection at warmer climate. So this model seems to support our hypothesis that there is this regulation of tropics by creating more clustering convection. Now, another way, I'm almost done. So just basically repeating Tobin et al. Kind of analysis. So now instead of like looking at the whole kind of tropics, all kind of individual clusters, PDFs, what I look at the area, at the regions of 10 by 10 degrees regions, of course not arbitrary, just some grid of them. So I divide it into regions, and then I look, using my algorithm, I look at number of clusters in this particular region, 10 by 10 degrees, which is about 1,000 by 1,000 kilometers, right? And then I count them. So for example, in this case, here is 6 clusters, and here it's 1 cluster in this region. And then you look at statistics, you look at PDF and stuff like that. So what's the result? And I compare it to Tobin et al. Paper observations, derived from observations, this cluster statistics. So what they show actually that in terms of if you have number of convective clusters here, so more aggregated is here, pure clusters in the region, and here is more clusters. So here is aggregation is going from right to left, more high degree of aggregation. You see that if you look at precipitable water or column amount of water in atmosphere, you see that as it aggregates, it's getting drier. So that's what we actually have seen, and that's what model also suggests. And in the model, for 3 different types of precipitation in this region, so basically, like let's say, look at 10, which is kind of more comparable to this, you see that this blue curve, so it shows the same behavior in the model, that as you increase, if you decrease number of clusters, you actually dry the region. So you have big clusters, dry atmosphere. That's exactly what's happening. And this is vertical profile of relative humidity. This is from observations from this study, and this is from the model that I use the same number of clusters. So as you see, they kind of agree with each other that as you increase degree of aggregation, your low level relative humidity doesn't really change, while your mid level and high level troposphere actually dries out, opening the sky. And OLR is just as you expect in observations. As you increase a degree of aggregation, your OLR is going up, so you open the sky, and the same happening in the model. I probably skip this one. This one is actually a fascinating topic, but fortunately I don't have time for that. And this is just a heads up, kind of for maybe next seminar. If I increase a domain, make it twice as big, then it's like whole tropics, then I can actually simulate MGO, medial oscillation. And my preliminary results actually show that I have actually MGO simulated in the domain. But I'm not going to talk about that. It's not really analyzed properly yet. Okay. So in summary, CRM is an expensive tool, but I think it's very powerful to simulate all this kind of interesting interaction among clouds, radiation, and water vapor, and to understand better how actually climate system works. Not because if you simulate it even with say 1 meter resolution, do you really understand anything? You have this bunch of pictures of clouds moving around, but without really looking at some idealized cases, you won't be able to actually understand if you just simulate actual, say, squall lines and stuff like that. It's very difficult to understand what's going on. So this kind of idealized simulations I like because they allow you to actually reduce complexity of the system and to see what's actually going on there behind all this clutter of other things. So tropics may be, it's our hypothesis that tropics is maybe in this kind of state, which is around critical state that would resist future global warming, and that would provide powerful negative feedback to warming. And that's what one of the things that I actually didn't show at the end, but actually looked at that. This mechanism is not in any GCM, general circulation models that do our kind of climate change simulations. So there are now attempts to actually put some mechanism like that in GCMs, and actually they see this that indeed with cluster, if you put more clustered convection in response to SST, you see decrease in the climate sensitivity of tropics. And so this aggregated convection serves as some kind of thermostat for tropical climate. And I think I'll finish here. Thank you.
Yeah, Marat, very interesting. I have two questions. One is about the size of the cyclones up under the warmer climate. Since under the warmer climate, we see more genesis, but we see less number of the cyclones. So, but you also see larger self-aggregation. So in that sense, do we see larger in size of those cyclones?
No, those are different. Like for example, these simulations, they don't produce any tropical cyclones. Because for tropical cyclones, you need to shift SST north or south. And when we do that, we start generating tropical cyclones like crazy. But I haven't shown those animations. So in this case, what I'm talking here is these clusters that are associated with tropical waves, deep tropics. Tropical cyclones provide very little in terms of overall effect on climate. I mean, they are of course very interesting things, and they can bring disaster. But I mean, in the overall scheme of things, they do very little. That's why most general circulation models that don't have tropical cyclones, they kind of able to reproduce kind of climate average climate quite all right, because so tropical cyclones is a little bit different, not quite related to this cluster.
Second one about the feedback, possible feedback, this self-aggregation back to the SST, because in your experiments you specify the ST, probably follow up, I this question. You specify the ST with a specific number, such as 300, 303.
Right.
But under the real situation, we have more clouds, we definitely will reduce the ST amount. There's some feedback inside.
Yes.
So under the climate model or system, this feedback, positive and negative feedback looks like. So we'll probably slow down this overall warming speed. So if we include this feedback in the model.
Yes, this one is again, it's an idealized study when you actually have present, which is kind of a relatively constant SST. If you look at the upsiding regions, not subsidence regions, but regions where you have convection, SST is very narrow range. It's like from 300 degrees to 302 degrees. Very narrow range. And then, so it's if you look at deep tropics, it's very regulated somehow. But so basically, that's what we're trying to capture here. Of course, there are again. You're talking about very important detail, but those I think details that not main issue.
Yeah, just to follow up on that, because you showed that the OLR actually increased a lot because of the drive, but then if you have short wave, then short wave will also increase. So that's the opposite direction.
That's very good. That's what I missed. That's one of those feedbacks that actually can cancel that effect. So in terms of here, in my results, that I didn't show in the interest of time, but albedo here. So you see that albedo is actually decreasing for aggregated state, which means that more actually going into
more short wave.
Right. So it's actually in a way it's opposite.
Yeah. So there's a cancellation.
Yeah. So that's actually what one of the ongoing research interesting, which effect actually winning.
So what's the net effect?
Well, here it's I didn't plot it. Here it's kind of, I would say it's about, I don't know, about washout. But the thing is, like, you see, big cluster can actually be more prominent at night when, like, let's say, it's only, you know, all are always operating. Shortwave is only during daytime. And during daytime, usually cluster activities subsides. So if you have more clusters developing at night, it actually would be a strong effect of OLR. So it's all, I know that in observations, it's basically canceling. Currently, like in Bonny and others, they demonstrated that this clustering effect actually at present climate is canceling. But it doesn't mean that it's gonna, that it would cancel in the future.
You're staying on the same topic. I don't think you use the term adaptive iris, but at least the OLR kind of looks like an adaptive iris, but if it's canceling, then maybe it isn't.
Yeah, that's what most important question right now that we try to address. Yes. Yeah, it's there is much more to this topic than I presented here.
Yeah. So you use the aggregation to imply the changing of the cyclone intensity number.
Yeah.
Now, in observation, the cyclone intensity and the size are not very well correlated. So the aggregation here is more like the size rather than the intensity.
No, in this in simulations in TC waters, they're not also very well correlated.
In the model, they are correlated.
No, not quite. No, bigger cyclones, not necessarily stronger ones. But I mean, overall, if you just, you see those cyclones are tiny at colder temperatures. So overall, when they become bigger, I'm talking about like at present. If you have the same SST, you have bigger cyclones and smaller ones at the same temperature. Bigger ones not necessarily stronger than smaller ones. But as SST changes, bigger ones become stronger on average than before. So that's different, two different, subtle different things.
Yeah, I also had the iris effect by Linson in mind as I saw your results, and he talked more about ice nucleation, dehydration of the upper troposphere. Just in context with your work, I see that you said the atmosphere opens up at higher altitudes, lower temperatures, and I guess that's where the ice phase is present, and that dehydrates most efficiently the surrounding atmosphere. Is that a valid statement? Is that crucial, your ice phase? Is it sensitive to that? Because you go higher altitude than 240 Kelvin, if you have more or less ice, you will have different dehydration up there. So could it be sensitive to these microphysics?
Yeah, it could be, but I think it's not main effect here. It's not main effect here. Here is radiation interaction with water vapor. That's the main effect. In clear skies.
Yeah, but the water vapor, you know, you have one ice crystal, it dehydrates everything.
Yeah, that's probably additional.
So the water vapor is gone most efficiently.
Yeah, I can't tell here because here it's very simple microphysics that I use.
Yeah, no,
so it's, yeah, but those could be important too. Yeah.
You know, so about this point regarding the reversal of radiation up to reduce the water vapor.
Right.
In your plot, you change the SST a lot,
right?
To 40 degrees. Now, in the real world, you said the SST does not change that much. It's only a few degrees. So that in that range, the reversal won't occur. Is that right?
Well, that's a good point. Yes, that probably is a little bit extreme change. It's about 10 degrees. But it's just to demonstrate kind of the point, to see it better. It doesn't really, even at few degrees, it doesn't nullify this effect. There is another possible mechanism for aggregation, which is not necessarily this instability, which is basically based on Vichy. So basically, a more organized convection creates more gustiness, more gust to the surface, which is this evaporative feedback. And that's another thing that we're trying to explore. And understand that which effect is actually more important.
Yeah, I think it's very interesting, but it's getting a bit late. So let's continue the discussion at lunch. Yeah.
I really underestimated. What? I really underestimated the amount of time I was using. Like I skip like half of it.
What did it?
Yeah, it doesn't work anymore.